the buffer cache in databases is super, super important for getting high performance out of your system. So I want to talk about how it works and how it helps make things faster when fulfilling queries in a SQL database. So we'll start by just looking at a B tree, right? In a database like MySQL, table data is in clustered indexes, which means your table data itself is actually in a B tree. In Postgres, it's done a little bit different, where it uses a table or a file with a bunch of pages in it that have your data, and then auxiliary indexes are used even for your primary key and for other indexes that point into this big table file. But we're gonna go with the example of having our table data itself be within a B tree. So I have what you might think of as a typical B tree here. The primary key, or the keys, are going to be the IDs of our row. So in my root node up here, I have like 20 and 40, and then I have an extra empty gap over there. And then I've got, this is a 3-level B tree. So then my second level has a few nodes. And then my third level is down here, and it's just all leaf nodes, right? And it's a really, really simple set of table data. So each row we're saying is just an ID and a name. So extremely basic, just to make it kind of fit on the screen better here. Throughout the process of a database running and doing lookups, right? If I say a query like the following, let's say I want to do select star from user where ID equals, let's do 17 down there. How is this going to be fulfilled? Well, we're going to find our root node, right? At some point we need our root node. We're going to say, okay, 17, we're going to compare this to the first key. It's less than that, so I'm going to follow this path down. And then we're going to look in here, 8, it's bigger than 8, it's bigger than 15. All right, I need to follow this path down, and then we find our row right there and can read that. So for this, if my database just needed to do reads from disk every single time it needed to do a lookup, it would have had to do a read for this page right here. So that's one. And then once it loads that into RAM, it goes through and it finds the right pointer to follow. And by following this pointer, it would have to then also read this element into memory. So now that's 2 reads. And then we would go down here, and then this one would be 3 reads. But now let's say we do another query. So now I want to look up the user with ID 12 down there. So that's Ian. So for this one, again, now it's a whole separate query. And if we have no in-memory buffering or caching, I would again have to find the root node, read this into memory, do my scan and figure out I need to follow this one. So notice I'm following the same path. I'm going to read this in again. If I want 12, I look at this and I look at this, and then I end up following this path down instead and reading this one in. So I ended up doing 2 different lookups. One of them was on the leaf page with 17. One of them was on the leaf page with 12. But the path to get there actually had 2 overlapping nodes. So if you look at this, it's kind of interesting. It would be kind of a waste for me to go read this one in, read this one in, read this one in, and then throw that all away. And then the next query on this table, I have to go read this in again, read this in again, but then I would be looking up a different node down here. There's got to be a smarter way to not always have to do reads, because even on an SSD, which is pretty fast, reading something from an SSD is still order of magnitude, if not more, maybe multiple orders of magnitude slower than reading something from fast like DDR5 RAM on your server. So one of the ways that we solve this is using an in-memory cache, an in-memory buffer, to save some of these pages and nodes of B trees that are commonly read, so that we can perform these lookups faster and do less IO on disk, which in turn makes our databases run faster. Okay, so I've got the B tree here in a little diagram showing the CPU, which when a query comes into my database, it's going to come to the CPU, right? And the CPU needs to parse the query. It needs to create a query plan, figure out what tables need to be looked up. And from there, then it needs to start doing the IO to like read in the appropriate pages. So what I'm going to do is I'll actually take this B tree here and we're going to bring it in, and it's going to look a little bit awkward, right? But really on disk, this B tree is it's not formatted, like it doesn't literally look like a tree. It just looks like a bunch of pages that have pointers to each other. But to keep things simple, I will just take this and we'll kind of put it in this SSD box to represent like this is what's on disk. All right, so a query comes in on the CPU. Let's say select star from users where ID is greater than 20, less than 40. So this is a scan and we want to do some ordering. So once the CPU has parsed that, we need to start doing IOs. And what would we be doing for this? Well, we would want to look at, first we need to get the root node of the B tree. So we're for sure going to have to load this in. So I'm going to do an IO to bring this in. But what I'm going to do is when I do that IO, I'm actually going to keep this page in my page cache, which this is RAM. So this is a chunk of RAM that has been specified as storage space for pages from your B tree. And then I'm going to mark this as, okay, it's in the cache. And then on disk, just going to color coordinate so that I know this is one that is in cache. So then the next time, like if this select is running, but then 10 seconds later, another select comes in on this same table, and it needs to start at the root node to do a search, it doesn't even have to go to disk. I already have a copy of it in RAM, and that's much faster, so I can just do that lookup. Okay, so then for this one, right, ID greater than 20, well, so we know we're not gonna have to go down this path over here, use orange, because those ones are all less than 20, but I'm gonna have to go down this path, and these ones are all greater than 40. So I know I'm only gonna have to go down this path for this query. So again, I'm gonna read this in, but I also know that I'm going to read it in, I'm gonna put it in my memory, my RAM, and then I'm gonna mark that one as, hey, I also have a copy of this in RAM. So the next time I need to query this one, I don't have to do this slow lookup, which, you know, doing something from SSD, these are, I'm using some ballpark figures, but that might be like 10 microseconds. You know, my numbers might be a little bit off there, whereas a RAM lookup is probably in the hundreds of nanoseconds, right? So 1 or 2 orders of magnitude, 10 times faster, 100 times faster doing this lookup. Okay, and so then to actually do the search, we'll just kind of skip ahead here. From between 20 and 40, I'm eventually going to have to read in this one. Oh, wait, I wanted orange here. I'm going to need to read in Tim, Cam, Win, Jim, and I guess none over there. So it's like these 4 rows, which are in 3 different pages. Okay, so this is where things start to get interesting. I will make this page cache for the sake of simplicity. It can only fit 3 pages. So we've got 1, 2, and there's room for 1 more. Okay, so we'll do our first read, which is this one right here. We're reading this for our query. I put it right there. I color code it green. So now that's in there. And again, if immediately after that someone else needed to look up Tim, it would be there. But now for this next one, I need to move on to this row right here. And my RAM is full, right? And this happens all the time in databases. You might fill up, you might have a 1 terabyte database, and you have 64 gigabytes of RAM that you've specified as your page cache, right? This is assuming a big server with a lot of RAM, but still 64 gigabytes, or, you know, if your whole server has 64 gigs, you might only use 50 of those for your page cache. So 50 gigs is 1/20th the size of your full 1 terabyte database. So there is, depending on the workloads, going to be times where you've filled up your whole page cache with pages to do fast lookups, but you'll sometimes have to make a choice and say, my page cache is full, but I need to load something new into the page cache, so you have to decide what to evict. In this case, we'll do something very simple. We'll say, well, the root node I'm probably pretty much for sure going to need again. And this one is a part of my scan that I might need to look at again. So I'm actually going to go ahead and evict Tim. So the nice thing is, because I haven't modified Tim, this is easy. I don't have to rewrite it to disk or anything. I'm just going to evict it. Boom, it's gone. But now I'm saying, hey, that one doesn't exist there anymore. And now I'm going to bring this in. So that one's in my cache, right? And so then the same process repeats. We read those 2 rows, but then I need this one. So I'm going to copy this. This one gets evicted. This one goes in here. This one is now my one that's in RAM. But essentially I have this mapping where subsets of my full data are in RAM, and there's this whole component called the buffer pool in MySQL is what it's called. I believe it's the I forget, I think page cache is not the right word. I'm blanking on the correct name for Postgres, but there's a similar mechanism in Postgres, but there's a subsystem of databases whose whole job it is to essentially manage this mapping between, I want to keep as many pages from disk as possible in RAM because it keeps things fast, but I can't fit everything in there. So how do I decide which things get kicked out when I need to replace something? Or let's look at one other example here, which is, let's say instead of doing this select, but now I'm going to run a different query called, update user set name equals John, where ID equals 37. Okay, so we're going to update this user. So I have this in RAM, and there's a whole side of this with the write ahead log as well, which I'm kind of ignoring for now. So we're going to simplify things. But I want to update this, which is one of my pages in memory, from Jim to John. And what I'm actually going to do in this case, and this is a trick a lot of databases use, is they will write a record to their log so that something is persisted to disk. So in the log, they'll say, hey, I updated row ID 37's name from Jim to John. So there's something persisted to disk. But then in terms of the actual B tree structure, all it will do is update this to John, and then we will mark it red, but this indicates this is a dirty page, which means that if I then go to evict this at some point, I can't just throw it out and put something new in there. I have to actually write this change to disk to make sure that the structure on disk is persisted before I can replace it with something new. So then if I come in with yet another select, and let's just do a select star from user where name equals, or let's just do ID, where ID equals 45, right, which is down on this path here, I will actually eventually have to evict multiple things, because I would go down here and I would say, okay, I'm looking at this node for the beginning of the search. Great, that's already in there. But now I know I have to go down this path because the ID is 45. So I have to decide something to evict. So let's say I decide to evict John. I have to make sure this goes down here and I update this page. So I'll just type it in here, JON. And again, this might seem simple, but it's costly because writes in databases take a lot more time than just reading and writing from RAM. So now that update is persisted. So now I can get rid of this, get that out of there. And then I will bring in this page into my page cache because I'm following down this way for my search. So now that is in there and this no longer is. So I no longer have any leaf nodes in my page cache. It's just internal nodes. And then I would know that I have to go down here and I have to evict something. And again, there's different algorithms for choosing what you evict, but because this is the more recent search path, I'm going to choose to evict this one this time. There's no updates to it, so I don't have to write it to disk, but now that's not in there. And I'm going to make a copy of this and bring this into my page cache, and then I keep that in sync. That actually really only scratches the surface because there's a lot to this, right? We came up with some very simple examples, but you have to consider many queries can be executing on this same table, doing lookups at the same time, right? Concurrency. What happens if while all of these transactions are happening, you might do insertions, which then trickles up to, well, I have to split an inner node, and it might even go so far up as having to split the root node. And how do you invalidate your cache when you actually have to do splits in your memory and making that sync with disk at the appropriate time? How this interplays with the log that I mentioned, which we haven't talked about much. And then again, the algorithms for actually choosing, right? There's better and worse algorithms. They're not all created equal for how you choose to evict something from RAM, because ideally you'd never want to evict something where 1 millisecond later you're just going to need to pull that same thing back into RAM. You always want to try to make the best choice for, I want to evict the thing that I won't need for the longest amount of time, but doing that perfectly is hard to do while you're also doing it efficiently time-wise. So this is really a fascinating area of databases. This only kind of scratches the surface, but gives you a good idea about how these things work in databases and why we need a page cache is because the reads and writes that we do to here happen order of magnitude or multiple orders of magnitude faster than reads and writes even from a solid state disk.